In this video, we are discussing substances that are gases. We will talk about the different types of gas laws. We will do calculations using these gas laws, and we're going to look at the different relationships between the variables that we talked about in our previous video: pressure, volume, temperature, and we will also talk about number of moles of gas. Here are the learning targets. Now, in our previous video, we started to talk about pressure. We've talked about volume and temperature before. When it comes to gases, all three of these variables are important: pressure, volume, and temperature. When we try to solve problems where we're given an initial condition and some final conditions, and we're trying to solve for one of the variables, we use what we call a combined gas law. And this formula that you see here is the combined gas law. P1V1 over T1 is equal to P2V2 over T2. P stands for pressure, V stands for volume, T stands for temperature, the 1 stands for initial, and 2 stands for final. As we go throughout this discussion, keep in mind the units for these variables. Pressure, you can see it as ATM, atmospheres, kPa, kilopascals, mmHg, millimeters of mercury, or torr. So remember, those are all pressure units. V, volume, will be in milliliters or liters. Sometimes you might have to convert them, sometimes you might not have to. And then temperature, remember, is in Kelvin. So we're not dealing with anything that is Celsius, but instead we have to convert everything that's Celsius into Kelvin. And remember how to do that? You add 273 to your temperature that's in Celsius in order to get Kelvin. So let's use this combined gas law and look at a few practice problems. Example 1. A gas occupies a volume of 20 liters at a pressure of 5 atmospheres and a temperature of 500 Kelvin. What will the volume be if both the pressure is raised to 10 atmospheres and temperature is changed to 250 Kelvin? So the first thing you want to do is identify the different variables that they're giving you, right? So I know that this is a combined gas law because they're giving me all the variables except for one, and they're giving me pressure, volume, and temperature. Okay, so we're gonna go through the problem again, and every time we hit a number, we're going to go ahead and write that down. So we're first identifying our variables, right? So a gas occupies a volume of 20 liters. That right there is V1. So I'm going to write that down next to V1. Pressure of 5 atmospheres. Again, that's the first pressure given, 5 atm. And a temperature of 500 Kelvin. What will the volume be if both the pressure is raised to 10 atmospheres and temperature is changed to 250 Kelvin? So we have pressure at 10 atmospheres and temperature at 250 Kelvin, and we are solving for volume. So now that we have everything, we want to go ahead and plug it into our formula. So you would have something like this once you plug everything in. Now we're trying to solve for volume 2, okay? And do you remember how to solve for this variable when it's set up like this? You have to think back to your algebra class. If you said cross multiply, that's exactly what we're going to do. So we're going to cross multiply. And once you cross multiply, you're going to set up your problem like this. 5 times 20 times 250 is equal to 500 times 10 times V2. And you can replace that V2 with X. That's completely up to you. So for this one, I'm going to go ahead and show you step by step how to solve for your variable. So volume, we have 5 times 20 times 250 divided by 500 times 10, right? Because you want to isolate your unknown. And you multiply and divide. Your units will cancel out, so atmospheres cancels out, Kelvin cancels out, you're left with liters, which is great because that's what the unit for volume is, or should be. And for volume, the second volume we have is 5 liters. So go ahead and pause the video now and try this problem on your own. Try to put it into your calculator before you move on. Example number 2. Now, my honor students, you guys don't have this on your paper, so feel free to use a scrap piece of paper and do these problems. I only gave you guys one example for a combined gas law, okay? So example number 2, a sample of nitrogen gas is stored in 500 milliliters flask at 108 kilopascals and 10 degrees Celsius. The gas is transferred to a 750 milliliter flask at 21 degrees Celsius. What is the pressure of the nitrogen in the second flask? So again, identify your variables, okay? 500 milliliters, that's volume 1. And this is also the reason why units are so important, especially during this topic, okay? So 500 milliliters is the initial volume. 108 kilopascals is the first pressure. 10 degrees Celsius is the first temperature. And that gas is transferred to a 750 milliliter flask, there's our volume 2, at 21 degrees Celsius. What is the pressure? Now, before we even think about plugging this in, we got to make sure that our units are appropriate, okay? So kilopascals, fine. Milliliters, as long as they both match up, fine. Because remember, once you multiply and divide, those milliliters will cancel out anyways. Now, the temperature. You see that the temperature here is degrees Celsius. And remember what I said earlier in this video and even in the previous unit? Temperature for gases cannot be Celsius, it's got to be Kelvin. So we're going to convert these temperatures first before we set it up in our formula. So to each one, we're going to add 273. So initial temperature, add 273 to 10 degrees Celsius, and you get 283 Kelvin. Temperature 2, do the same thing, and we get a total of 294 Kelvin. Now we can plug it in. So you plug everything in. Again, you're going to cross multiply, and this time we're solving for the second pressure. Go ahead and pause the video and put it into your calculator and see what you get. And pressure 2 is 74.8 kilopascals. If you are considering significant digits, then the answer would be 70 kilopascals. Example number 3. A gas occupies a volume of 200 liters at a pressure of 2 atmospheres and a temperature of 300 Kelvin. What will be the volume if the pressure is raised to 10 atmospheres and a temperature is changed to 1000 Kelvin? Go ahead and identify all your variables. For this problem, I want you to try to do this one on your own. So go ahead and pause here, and when you're ready for the answer, you're going to unpause it. And you should have an answer of 12 liters for volume 2. If you're considering significant digits, then volume would just be 10 liters. Now sometimes we can keep one variable constant. Now this wouldn't realistically happen. Realistically, we would be looking at all 3 variables for all the gases, any type of gas. But we can, when we make one variable constant, we can look at the relationship between 2 variables. So if we were to keep temperature constant, we would just look at pressure and volume and look at what kind of relationship that is. We can keep pressure constant and look at volume over temperature, volume and temperature, and see what kind of relationship that has. And the last one that we can keep constant is volume, and so we would look at pressure and temperature. And this is what we're going to look at next. Now the first relationship we're going to look at is between pressure and volume. And I'm going to show you a YouTube video by Flynn. And I want you to think about these 3 questions as you watch it. What happened to the marshmallow when the plunger was pulled out? What happened when the plunger was pushed in? What happened to the pressure inside when the plunger was pulled out? And what happened to the pressure inside the syringe when the plunger was pushed in? And then do you think you can figure out the relationship between pressure and volume before I even tell you the answer? Okay?
Let's do something to the marshmallow, which is... Oh, but that's not how he's feeling. I got a glare.
So what happened to the marshmallow when the plunger was pulled out? The marshmallow expanded, right? It got bigger. And what happened when the plunger was pushed in? I don't know if it was obvious in the video, but the marshmallow actually shriveled. It shrunk a little bit. So what do you think was happening to the pressure inside the syringe when the plunger was pulled out? Do you remember in the previous video what creates pressure? What is happening with the gas molecules in order to create this pressure? Collisions, right? That's the key word there. The gas molecules need to collide not only with themselves, but also the walls of whatever container that they're in. The more collisions there are, the more pressure there is. The less collisions, less pressure. Okay? So what do you think happens to the pressure inside the syringe when the plunger is pulled out? Because there's more space when the plunger is pulled out, there are less collisions, right? So it's less pressure. When the plunger is pushed in, then it creates more pressure because there are more collisions between the gas molecules. So I know you can't see gas molecules, but going back to this PhET simulation, to show you what happens to the collisions of the gas molecules, so focus on pressure, and I'm going to change the volume. So right now the pressure is at right around 14, teetering back and forth. Now if I make the volume smaller, what happened to the pressure? Yeah, it increased to 27, 28, right? Because, and even if you look here, it's creating more collisions. What's going to happen when I bring the volume out? Less collisions means less pressure, right? It's going back and forth between 10 and 11 atmospheres. So what is the relationship between pressure and volume? If the volume increases, like I have in the simulation, then the pressure decreases. And if the volume decreases, then the pressure increases. What kind of relationship is that? Is that going back to our algebra class, is that a direct relationship or indirect and inverse relationship? Right, it's an inverse relationship. This is called Boyle's Law. Boyle's Law looks at pressure and volume, so we're keeping temperature constant. So Boyle's Law shows P and V, pressure and volume, as an inversely proportional relationship. It's an inverse relationship. If one goes up, the other goes down. It's an opposite relationship, right? So Boyle's Law is pressure 1, initial pressure, times initial volume is equal to the final pressure times the final volume. So think about Boyle's Law, and let's take a look at our first example. A helium-filled balloon is released into the sky. Assuming constant temperature, what happens to the volume of the balloon as the balloon goes up in elevation? And remember that as you go up in elevation, there's more pressure. So if there's more pressure, what does that mean about volume? If it's an indirect or inverse relationship. More pressure means lower volume, right? So the volume of the balloon decreases. Let's take a look at a mathematical type of example. A sample of helium gas in a balloon is compressed from 4 liters to 2.5 liters at constant temperature. If the pressure of the gas in the 4-liter volume is 210 kilopascals, what would the pressure be at 2.5 liters? So the first thing that you want to do is, again, identify your variables, right? So we have the first thing in the problem, they talk about volume. So we have volume 1 as 4 liters and volume 2 as 2.5 liters. The pressure of the gas in the 4-liter volume is 210 kPa, kilopascals. What will the pressure be at the 2.5 liters? So we are trying to figure out the final pressure. Okay, so we have P1, V1, P2, V2. I'm going to go ahead and use Boyle's Law, plug it all in, solve for P2, and we get 336 kilopascals. If you consider significant digits, we have 340 kilopascals. Next, we're going to look at volume and temperature. And think about these two questions as I show you the next YouTube clip. What happened to the water level when the flame on the candle went out? When the flame diminishes, what happens to the temperature?
Sit over top of the candles. After a little while of having our beaker over our candles, you'll notice the candle's flames will get smaller and smaller until they're extinguished. If you watch closely, you'll see that the water level underneath our beaker begins to rise as the candles fade away. The water level will continue to rise for a short time after the candle has been fully extinguished. You'll notice that the water underneath the beaker is much higher than the water in the shallow dish.
So you saw what happened to the water level, right? The water level inside the beaker went up. So think about it. When the flame goes out, what's actually happening to the temperature? Does it get hotter or does it get cooler? Well, when the flame goes out, it gets cooler, right? So let's talk about what we saw. So remember when we were in class, what do we need in order to make a fire? And you can think about the combustion reaction. You need oxygen, right? So in this case, we're talking about oxygen gas, okay? So when we created that space inside the beaker, all that oxygen gas was trying to take up more space, okay? So remember, pressure is held constant here, okay? So then as we close the space and the fire diminishes as the temperature goes down, in this case, it was actually more carbon dioxide and water that was being produced, and so there was less oxygen inside. And so at one point, the air pressure on the outside became stronger than the pressure on the inside. So because pressure was trying to stabilize, the air pressure basically on the outside of the beaker was pushing the water, and therefore the water inside went up. Now, if you think about volume and temperature, and again, I'm going to use a simulation, pressure is held constant. If I heat it up, you see that nothing happens to the pressure. I did not pump more gas molecules in there, but you saw what happening to the volume. The volume was increasing, right? And then if I cooled it down, and again, pressure doesn't move, right? When I cool it down, then what happened to the volume? It went down. So what kind of relationship can we explain volume and temperature? It's a direct relationship. If one goes up, the other goes up. If temperature goes up, then volume goes up. If temperature goes down, then volume goes down. This is known as Charles's law. V1 over T1 is equal to V2 over T2, and here we have a direct relationship between these two variables. If we increase the temperature, volume also increases. If we cool down the temperature, then the volume also goes down. The first example we see is that a basketball is left outside. If the temperature dropped from 50 to 25 degrees Celsius, what happened to the volume of the basketball, assuming constant pressure? So we can pretend that it's fall or winter, right? The temperature goes down and the basketball stays outside. What's going to happen to the basketball? It's going to shrink, right? So temperature goes down, volume goes down, and in this case, the volume of the basketball will decrease by half. Let's take a look at a calculation kind of example. A gas sample at 40 degrees Celsius occupies a volume of 232 milliliters. If the temperature is raised to 75 degrees, what is the volume assuming the pressure remains constant? So again, let's identify our variables. We have temperature 1 as 40 degrees, we have volume 1 as 232 milliliters, temperature 2 is 75 degrees. What is volume 2? Okay, now what do I have to do here before I even set it up? Right, I have to change the temperature to Kelvin. So to each one, let's add 273. So we have a new temperature, initial temperature of 313 Kelvin, and a new final temperature of 348 Kelvin. So let's go ahead and put it into the formula for Charles's law. V1 over T1 is equal to V2 over T2. And how do we solve for volume 2? Again, you're going to cross multiply just like we did before, okay? And volume 2 is 258 milliliters. So go ahead and pause the video here because I want you to try to put that into your calculator and get that same exact answer. All right? The next one we're going to look at is between pressure and temperature. And I'm going to show you another YouTube clip. And it's going to use an aluminum can, and you'll see what happens to the aluminum can. And these are the 4 questions that I want you to think about. As the can is heated, Think about what's happening to the air and water molecules inside the can. How about when it's placed in cold water? What happened to the pressure when it was heated? What happened to the pressure when it was cooled? Okay. Think about air pressure, the pressure that's all around us. And lastly, then what do you think is the relationship between pressure and temperature? So again, remember where pressure comes from, right? It's the collisions of the gas molecules. The more collisions there are, the more pressure there is. The less collisions there are, the less pressure there is. Now you guys could definitely try that experiment at home. If we were in class, we would have also done it in class. Just make sure that you are using some of those kitchen tongs to handle the aluminum can. And yes, it has to be an aluminum can, and you only want a little bit of water inside the can. So go ahead and try that if your parents will allow you to. So let's talk about what happened. As the can is being heated, what is happening to the air and water molecules inside the can? So if you have a little bit of water inside and you're heating it up, well, what's happening to that liquid water? Right, it's evaporating, right? And as it evaporates, because there's only a small hole in there, I mean, really most of it is still inside. And as it evaporates, as it changes into a gas phase, into a vapor phase, what is happening to those gas molecules? There are more collisions, right? And if there are more collisions, what's happening to the pressure inside? It's increasing. So then what happens when you all of a sudden invert that can and put it into cold water? What's happening inside? Well, the gas molecules suddenly get cooled down, then the number of collisions actually slows way down, right? So if it slows down, what's going to happen to the pressure inside, right? It decreases drastically, okay? So remember, there's air pressure all around us. So what do you think crushed the can? It wasn't the kitchen tongs that they used, but it was actually the air pressure that crushed the can, because at that moment right there, the air pressure is stronger than the pressure inside the can. So if we look at this simulation here and I heat up this sample here and volume remains constant, what is happening to the pressure? Yeah, you can see that the molecules are moving faster. Faster moving molecules means more collisions leads to more pressure. And then we cool it down, you can see that the molecules are starting to slow down. Slowing down means less collisions, less collisions means less pressure, right? So what is the relationship between pressure and temperature? It's another direct relationship. If we increase the temperature, then we increase the pressure of the gas. If we lower the temperature, then we lower the pressure of the gas. This is known as Gay-Lussac's law. So Gay-Lussac looked at pressure and temperature, where volume remains constant, and here we have another direct relationship. Temperature goes up, temperature goes down, then the pressure goes down. Let's take a look at this example. What happens to the tire pressure during the winter season, assuming there are no leaks in the car tires? You guys are starting to drive. Your parents might have already gone through this experience this past winter. You know that the tire pressure actually goes down. Okay, sometimes we get a light on our dashboard saying low tire pressure, and then you have to put in some pressure, right? So that's what happens. Pressure goes down because it is so cold. It's a direct relationship. Example 2. A sample of neon is at 89 degrees Celsius in standard pressure. If the pressure changes to 145 kilopascals and the volume remains constant, find the new temperature. Well, let's define our variables. We have 89 degrees as our initial temperature. What about our initial pressure? If you said 145 kilopascals, gotta think again. The initial pressure is actually at standard pressure. So this is from our previous video. But what is standard pressure? If you said 1 atmosphere, 1 atm, you're absolutely right. But what is the pressure unit for this problem? It's not atmospheres, but instead it's kilopascals, right? So the standard pressure for kilopascals, do you remember, is 101.3 kPa. And then pressure 2 is given. And we're trying to figure out the temperature. Add 273 to convert it to Kelvin. We have 362 Kelvin. And let's set it up. P over T is equal to P over T. We're going to cross multiply to determine the final temperature. And we get a final temperature of 518 Kelvin. Now, for this particular problem, I just want to quickly mention, your temperature is already out Kelvin. You don't need to add 273 again. You don't need to subtract 273 again. You wouldn't do that at all because, again, it is out Kelvin. We don't ever want Celsius, so please don't convert it back to Celsius, okay? Now, to help you remember these 3 gas laws and the 3 relationships, we have a triangle here. Some of you guys might have done this for density, D equals M over V. This time we're going to do it with the combined gas law. And you draw a triangle with an upside down T, and you plug in the variables P, V, and T. And the way that this works, I mean, this is really for the 3 gas laws we just talked about, Boyles Law, Charles' Law, and Gay-Lussac's Law. Let's say you're reading a problem, whether it's a concept question or a math question. And it's talking about, it's giving you pressure and volume, and it's not talking about temperature. We're going to cover that up. That right there tells you the formula. P times V. P1 V1 is equal to P2 V2. That is Boyle's Law. Let's say it's another problem. They give you volume and temperature, and they don't give you pressure. Let's cover it up. Well, what does that look like? V over T. V1 over T1 is equal to V2 over T2. There's Charles's Law. Last one, but the problem gives you pressure and temperature, doesn't give you volume. That right there is Gay-Lussac's Law. Okay, so this is to help you remember the 3 different laws and the 3 different formulas and the 3 different relationships. Okay.